Hello everyone, and welcome to another worked example in the section 3.1 Thermal Concepts. This is worked example 3.4 from page 121. An ice cube of mass 25 grams and temperature minus 10 degrees Celsius is dropped into a glass of water of mass 300 grams and temperature 20 degrees Celsius. Calculate the final temperature. So after the ice and the water have been together for a while, they will reach their own final temperature, which will be the same for both. We're told the specific heat capacity of water is 2200 joules per kilogram per Kelvin. The specific latent heat of fusion of ice is 334 joules per kilogram, and the specific heat capacity of water is 4200 joules per kilogram per Kelvin. This would be a good time to point out that in the textbook, they have written that the latent heat of fusion of ice is 334 joules per kilogram per Kelvin. That is incorrect. You cannot have a latent heat per unit temperature, because the whole point of latent heat is that as you add heat to the system, it is hidden since the temperature doesn't change. So it's just a typo, which I've corrected in this part. There is actually another problem with the solution to the question in the book, but I will be doing the correct solution in this video. So you have two media here. You have ice and you have water. So let's write down what we know. Okay, we know that the ice is 25 grams, so M sub I. And I know in another video I did I was iron, now I is ice. So that's 25 grams. I need to convert that to kilograms, so that's 0.025 kilograms. So effectively what I did is I divided it by 1,000, or seen another way, I took the decimal and moved it to the left 3 spaces. Okay, I'm told the mass of the water is 300 grams, so M sub W is 300 grams. And converting that to kilograms, that's 0.300 kilograms. We don't really need to worry about sig figs. Now the ice cubes initially at a temperature of minus 10 degrees Celsius. So initial temperature of the ice, minus 10 degrees Celsius. The initial temperature of the water is 20 degrees Celsius. Calculate the final temperature. Now there's a lot of stuff happening here. Let's, I guess, write down these specific heat capacities first. Specific heat capacity for the ice is 2200 joules per kilogram per Kelvin. And if you watch the other worked example video, I said that for every increase in 1 Kelvin in temperature, you're increasing the temperature also by 1 degree Celsius. Okay, if you decrease by 1 degree Celsius, you're decreasing by 1 Kelvin. So by saying that the specific heat capacity or latent heat, or actually not latent heat, if you're saying the specific heat capacity is per Kelvin, that's the same thing as saying it's per degree Celsius. Excuse me. So joules per kilogram per degree Celsius. And you know what, I'll just do that for water right from the get-go. So CW is 4200 joules per kilogram per degree Celsius. And we also know the latent heat of fusion of ice, 334 joules per kilogram. Okay. Now, this problem is going to take more work than the one in the PowerPoint. So when we had the gentleman in the video, in the PowerPoint, who made a chair out of ice, he needed to figure out how much energy to remove from water in order for it to turn into ice. The difference was between that and this question is that not only was he going from water to ice instead of ice to water, which isn't a big deal, but the water was already at the freezing temperature. So all you needed to do was remove heat from it and you could get ice. Right now, the ice is at minus 10 degrees Celsius. So first things first, I mean, if you put the ice into water, it's going to start to melt, right? So that ice at minus 10 degrees Celsius, it's going to melt until it reaches 0 degrees Celsius, right? So that ice is now going to be at 0. Now that the ice has reached 0 degrees Celsius, I guess it'll still be in its ice stage, it's going to start to melt. And it's going to start to melt to become water. Now, until all of the ice becomes water, it's going to remain at 0 degrees Celsius. Now, once all of the ice has become water, now the water can start heating up. So I guess actually we won't put such a rigid box around it. The water will start heating up to some new final temperature, which is still water. Okay, by the way, this is the original piece of ice. So it starts at minus 10, it increases temperature to 0, thereby gaining the heat energy Q1, which is Q equals MC delta T. Then when it has a phase change from ice to water, its temperature is constant at 0 degrees. We have latent heat. Q2 is equal to ml. And finally, as it changes temperature from 0 to whatever final temperature it's going to reach in its water state, we have Q3, which is mc delta T. This is a new delta T, this is another delta T. So we can call this delta T2, delta T1. So these three increases in heat for the ice is what the water is going to lose. Now, we don't actually expect the water to change temperature that much because after all, we have 300 grams of water and 25 grams of ice. It's a very small ice to water ratio, so it's not going to cool down substantially. Okay, so overall, the change in the heat of the ice is going to equal to the negative change in heat of the water. And you can make this kind of statement as long as one is gaining heat and the other loses exactly the same amount of heat. Now, like I said for the other worked example, we are ignoring cases like the heat is lost to the container or it's lost due to the surroundings. We are assuming that all the heat energy lost from the water is gained by the ice. So in this case, the heat energy is traveling from water to ice. It's always traveling from the warmer to the cooler object. So, like I said earlier, for the ice, it's gaining heat originally, so Q1 when the ice goes from -10 to 0, and then it's going to gain heat again as it undergoes its phase change, Q2, and then from 0 to whatever final temperature it's going to reach, which is what we need to find, it's going to gain energy again, so Q1 plus Q2 plus Q3. Now, the water starts at 20, it doesn't undergo a phase change, it's just going to cool down a little bit. So that's just going to be equal to minus mc delta T. And we know that the initial temperature in that delta T is 20 degrees, and we know that the final temperature is what we're looking for. That final temperature, which we're missing here, is the same final temperature in Q3, which appears right there. Okay, so this is water, M water, C water, delta T water. So Q1, that's equal to mc delta T1, and that's for ice, plus m ice times latent heat of fusion of ice for Q2, plus mc delta T2. So that's m ice, C ice. And that's equal to minus mw, Cw, delta Tw. So the reason this question has more going on than the previous one is because you have to take into account everything that needs to take place before it can reach that final temperature. And that's what we've done here. Okay, so the mass of the ice, actually we're going to use the kilogram one, 0.025 kilograms. C is 2200. Delta T, so it's going from -10 to 0. So that's an increase in temperature of 10 degrees Celsius. So we're going to stick that in there. Plus, again, mass of ice, the mass is not changing. So 0.025 times the latent heat of fusion of ice, that's 334. Plus, once again, mass of ice. So this is now when it's turning from water into, well, still water, but some new temperature. 0.025 times 2200 times T final minus T initial. Now, what temperature is it initially before it starts increasing? It's at 0. So 0 degrees Celsius. I don't even need to write that, but I'll write it just for thoroughness. Equals to minus M, so that's minus 0.3 times C water, 4200, times delta T. So T final minus T initial, which is 20 degrees Celsius. Notice the T finals are the same. So this is just a lot of stuff to punch in our calculator. So I'm going to do these first two products and get the value. So here we go. Okay, I don't think I can, well, actually, let's do it like that. There we go. 0.025 times 2200 times 10 plus 0.025 times 334 equals 558.35. So these two put together make 558.35. Okay, now let's do this next part here. 0.025 times 2200, that's 55. So plus 55 T sub F, and then it would be minus 0 times this, which is 0, equals 0.3 times 4200. Be very careful with that negative sign. If you forget that minus sign, your whole answer is going to change. Okay, so we have minus 1260, and then TF minus 20. So that trick I showed in the other worked example, you can get rid of the minus sign here by flipping the difference here. So we can write 558.35 plus 55 T sub F is equal to positive 1260 times 20 minus TF. Yeah, so you can choose to do that if you want. So now we have 1260 times 20, which is 25,200. So 558.35 plus 55 TF is equal to 25,200 minus 1260 TF. Okay, at this point, we have to collect our like terms. So we have TF here and TF here. Bring the negative TF on the right over to the left. So we have 55 plus 1260, that's 1315 T sub F. And take that 25,200 on the right and subtract from it the positive 8.35 on the left. So 24,641.65. So take that and divide it by 1315. And we get 18.7 degrees Celsius. So that is pretty reasonable. So the temperature in the water dipped a bit, not substantially. Unfortunately, in the textbook, there is a mistake. So let me just quickly show you where that is. Okay, so the worked example is this one right here, 3.4. So we turn the page. Oh, by the way, that first error is right here. It says per Kelvin. The online version I noticed is a little different than this one, so it might have that changed. That might just be in my version. So maybe it's just in my hard copy. I don't know. If the electronic version is updated and corrected, then that's fantastic. So they end up with 11.9 degrees Celsius. And the reason for that is when they're calculating the three heats that they're adding together, Q1 plus Q2 plus Q3, everything is fine except because here, when they're calculating Q2, the latent heat, they have M times L, and then they have times 10 to the 3. So that's a bit of a problem. So essentially you're throwing in an extra factor of 1,000 there, and when things get added up and then divided and subtracted later, it ends up with the wrong answer, unfortunately. So anyways, if any of you are wondering why the numbers don't match up, that's why. But I hope this answer does make more sense to you. After all, like I said in the beginning, you're starting off with 300 grams of water. You're adding a 25-gram ice cube. 25 goes into 100 4 times, so it goes into 300 12 times. So 1/12 of the matter is ice to water. So you wouldn't expect the temperature to go down by half. You would expect it to go down just by a little bit. Okay, so there is the solution to worked example 3.4. If you have any questions on that, be sure to let me know.